In quantum mechanics, perturbation theory is a set of approximation schemes directly related to mathematical perturbation for describing a complicated quantum system in terms of a simpler one. The idea is to start with a simple system for which a mathematical solution is known, and add an additional, perturbing, Hamiltonian representing a weak disturbance to the system. If the disturbance is not too large, the various physical quantities associated with the perturbed system can be expressed as corrections to those of the simple system. These corrections, being small compared to the size of the quantities themselves, can be calculated using approximate methods such as asymptotic series. The complicated system can therefore be studied based on knowledge of the simpler one. Perturbation theory is applicable if the problem at hand cannot be solved exactly, but can be formulated by adding the small term to the mathematical description of the exactly solvable problem. Applications of perturbation theory. Perturbation theory is an important tool for describing real quantum systems, as it turns out to be very difficult to find exact solutions to the Schrödinger equation for Hamiltonians of even moderate complexity. The Hamiltonians to which we know exact solutions, such as the hydrogen atom, the quantum harmonic oscillator and the particle in a box, are too idealized to adequately describe most systems. For example, by adding a perturbative electric potential to the quantum mechanical model of the hydrogen atom, we can calculate the tiny shifts in the spectral lines of hydrogen caused by the presence of an electric field. This is only approximate because the sum of a Coulomb potential with a linear potential is unstable, although the tunneling time is very long. This instability shows up as a broadening of the energy spectrum lines, which perturbation theory fails to reproduce entirely. The expressions produced by perturbation theory are not exact, but they can lead to accurate results as long as the expansion parameter, say alpha, is very small. Typically, the results are expressed in terms of finite power series in alpha that seem to converge to the exact values when summed to higher order. After a certain order n tilde 1 alpha, however, the results become increasingly worse since the series are usually divergent. There exist ways to convert them into convergent series, which can be evaluated for large expansion parameters, most efficiently by variational method. In the theory of quantum electrodynamics, in which the electron-photon interaction is treated perturbatively, the calculation of the electron's magnetic moment has been found to agree with experiment to 11 decimal places. In QED and other quantum field theories, special calculation techniques known as Fineman diagrams are used to systematically sum the power series terms. Under some circumstances, perturbation theory is an invalid approach to take. This happens when the system we wish to describe cannot be described by a small perturbation imposed on some simple system. In quantum chromodynamics, for instance, the interaction of quarks with the gluon field cannot be treated perturbatively at low energies because the coupling constant becomes too large. Perturbation theory also fails to describe states that are not generated adiabatically from the free model, including bound states and various collective phenomena such as solitons. Imagine, for example, that we have a system of free particles, to which an attractive interaction is introduced. Depending on the form of the interaction, this may create an entirely new set of eigenstates corresponding to groups of particles bound to one another. An example of this phenomenon may be found in conventional superconductivity, in which the phonon-mediated attraction between conduction electrons leads to the formation of correlated electron pairs known as Cooper pairs. When faced with such systems, one usually turns to other approximation schemes, such as the variational method and the WKB approximation. This is because there is no analog of a bound particle in the unperturbed model, and the energy of a soliton typically goes as the inverse of the expansion parameter. However, if we integrate over the solitonic phenomena, the non-perturbative corrections in this case will be tiny, of the order of exp or exp in the perturbation parameter G. Perturbation theory can only detect solutions close to the unperturbed solution, even if there are other solutions for which the perturbative expansion is not valid. The problem of non-perturbative systems has been somewhat alleviated by the advent of modern computers. It has become practical to obtain numerical non-perturbative solutions for certain problems, using methods such as density functional theory. These advances have been of particular benefit to the field of quantum chemistry. Computers have also been used to carry out perturbation theory calculations to extraordinarily high levels of precision, which has proven important in particle physics for generating theoretical results that can be compared with experiment. Time-independent perturbation theory. Time-independent perturbation theory is one of two categories of perturbation theory, the other being time-dependent perturbation. In time-independent perturbation theory, the perturbation Hamiltonian is static. Time-independent perturbation theory was presented by Erwin Schrödinger in a 1926 paper, shortly after he produced his theories in wave mechanics. In this paper, Schrödinger referred to earlier work of Lord Rayleigh, who investigated harmonic vibrations of a string perturbed by small inhomogeneities. This is why this perturbation theory is often referred to as Rayleigh-Schrödinger perturbation theory. First-order corrections. We began with an unperturbed Hamiltonian H0, which is also assumed to have no time dependence. It has known energy levels and eigenstates, arising from the time-independent Schrödinger equation. For simplicity, we have assumed that the energies are discrete. The superscripts denote that these quantities are associated with the unperturbed system. Note the use of bracket notation. We now introduce a perturbation to the Hamiltonian. Let V be a Hamiltonian representing a weak physical disturbance, such as a potential energy produced by an external field. Let lambda be a dimensionless parameter that can take on values ranging continuously from 0 to 1. The perturbed Hamiltonian is the energy levels and eigenstates of the perturbed Hamiltonian are again given by the Schrödinger equation. Our goal is to express n and in terms of the energy levels and eigenstates of the old Hamiltonian. If the perturbation is sufficiently weak, we can write them as power series in lambda, where when lambda equals 0, these reduce to the unperturbed values, which are the first term in each series. Since the perturbation is weak, the energy levels and eigenstates should not deviate too much from their unperturbed values, and the terms should rapidly become smaller as we go to higher order. Substituting the power series expansion into the Schrödinger equation, we obtain expanding this equation and comparing coefficients of each power of lambda results in an infinite series of simultaneous equations. The zeroth order equation is simply the Schrödinger equation for the unperturbed system. The first order equation is operating through by. The first term on the left-hand side cancels with the first term on the right-hand side. This leads to the first order energy shift. This is simply the expectation value of the perturbation Hamiltonian while the system is in the unperturbed state. This result can be interpreted in the following way. Suppose the perturbation is applied, but we keep the system in the quantum state, which is a valid quantum state though no longer an energy eigenstate. The perturbation causes the average energy of this state to increase by. However, the true energy shift is slightly different, because the perturbed eigenstate is not exactly the same as. These further shifts are given by the second and higher order corrections to the energy. Before we compute the corrections to the energy eigenstate, we need to address the issue of normalization. We may suppose, but perturbation theory assumes we also have. It follows that at first order in lambda, we must have, since the overall phase is not determined in quantum mechanics, without loss a generality we may assume is purely real. Therefore, and we deduce to obtain the first-order correction to the energy eigenstate, we insert our expression for the first-order energy correction back into the results shown above of equating the first-order coefficients of lambda. We then make use of the resolution of the identity, where the in the orthogonal complementive. The result is, for the moment, suppose that the zeroth-order energy level is not degenerate, i.e., there is no eigenstate of H0 in the orthogonal complement of with the energy. We multiply through by, which gives and hence the component of the first-order correction along, since by assumption. In total we get the first-order change in the nth energy eigenket has a contribution from each of the energy eigenstates kn. Each term is proportional to the matrix element, which is a measure of how much the perturbation mixes eigenstate n with eigenstate k. It is also inversely proportional to the energy difference between eigenstates k and n, which means that the perturbation deforms the eigenstate to a greater extent if there are more eigenstates at nearby energies. We see also that the expression is singular if any of these states have the same energy as state n, which is why we assume that there is no degeneracy. Second-order and higher corrections, we can find the higher-order deviations by a similar procedure, though the calculations become quite tedious with our current formulation. Our normalization prescription gives that up to second order, the expressions for the energies and eigenstates are. Extending the process further, the third-order energy correction can be shown to be corrections to fifth order and fourth order in compact notation if we introduce the notation. Then the energy corrections to fifth order can be written and the states to fourth order can be written. All terms involved kj should be summed over kj such that the denominator does not vanish. Effects of degeneracy. Suppose that two or more energy eigenstates are degenerate. The first-order energy shift is not well defined, since there is no unique way to choose a basis of eigenstates for the unperturbed system. The calculation of the change in the eigenstate is problematic as well, because the operator does not have a well-defined inverse. Let D denote the subspace spanned by these degenerate eigenstates. No matter how small the perturbation is, in the degenerate subspace D the energy differences between the eigenstates H0 are zero. So complete mixing of at least some of these states is assured. Thus the perturbation cannot be considered small in the D subspace, and in that subspace the new Hamiltonian must be diagonalized first. These correct perturbed eigenstates in D are now the basis for the perturbation expansion, where only eigenstates outside of the D subspace are considered to be small. For the first-order perturbation we need to solve the perturbed Hamiltonian restricted to the degenerate subspace D simultaneously for all the degenerate eigenstates, where are first-order corrections to the degenerate energy levels. This is equivalent to diagonalizing the matrix. This procedure is approximate, since we neglected states outside the D subspace. The splitting of degenerate energies is generally observed. Although the splitting may be small compared to the range of energies found in the system, it is crucial in understanding certain details, such as spectral lines in electron spin resonance experiments. Higher-order corrections due to other eigenstates can be found in the same way as for the non-degenerate case. The operator on the left-hand side is not singular when applied to eigenstates outside D. So we can write, but the effect on the degenerate states is minuscule, proportional to the square of the first-order correction. Near-degenerate states should also be treated in the above manner, since the original Hamiltonian won't be larger than the perturbation in the near-degenerate subspace. An application is found in the nearly free electron model, where near-degeneracy treated properly gives rise to an energy gap even for small perturbations. Other eigenstates will only shift the absolute energy of all near-degenerate states simultaneously. Generalization to multi-parameter case. The generalization of the time-independent perturbation theory to the case where there are multiple small parameters in place of lambda can be formulated more systematically using the language of differential geometry, which basically defines the derivatives of the quantum states and calculate the perturbative corrections by taking derivatives iteratively at the unperturbed point, Hamiltonian and force operator from the differential geometric point of view. A parameterized Hamiltonian is considered as a function defined on the parameter manifold that maps each particular set of parameters to an Hermitian operator H that acts on the Hilbert space. The parameters here can be external field, interaction strength, or driving parameters in the quantum phase transition. Let n and be the nth eigenenergy and eigenstate of H respectively. In the language of differential geometry, the states form a vector bundle over the parameter manifold, on which derivatives of these states can be defined. The perturbation theory is to answer the following question. Given n at an unperturbed reference point, how to estimate the n and at x mu close to that reference point, without loss of generality. The coordinate system can be shifted, such that the reference point is set to be the origin. The following linearly parameterized Hamiltonian is frequently used if the parameters x mu are considered as generalized coordinates. Then f mu should be identified as the generalized force operators related to those coordinates. Different indices mu label the different forces along different directions in the parameter manifold. For example, if x mu denotes the external magnetic field in the mu direction, then f mu should be the magnetization in the same direction. Perturbation theory as power series expansion. The validity of the perturbation theory lies on the adiabatic assumption, which assumes the eigenenergies and eigenstates of the Hamiltonian are smooth functions of parameters such that their values in the vicinity region can be calculated in power series of the parameters. Here mu denotes the derivative with respect to x mu. When applying to the state, it should be understood as the covariant derivative if the vector bundle is equipped with non-vanishing connection. All the terms on the right-hand side of the series are evaluated at x mu equals 0, e.g., nn. This convention will be adopted throughout this subsection, that all functions without the parameter dependence explicitly stated are assumed to be evaluated at the origin. The power series may converge slowly or even not converge when the energy levels are close to each other. The adiabatic assumption breaks down when there is energy level degeneracy, and hence the perturbation theory is not applicable in that case. Helman-Fineman theorems. The above power series expansion can be readily evaluated if there is a systematic approach to calculate the derivates to any order. Using the chain rule, the derivatives can be broken down to the single derivative on either the energy or the state. The Helman-Fineman theorems are used to calculate these single derivatives. The first Helman-Fineman theorem gives the derivative of the energy. The second Helman-Fineman theorem gives the derivative of the state. For the linearly parameterized Hamiltonian, mu h simply stands for the generalized force operator f mu. The theorems can be simply derived by applying the differential operator mu to both sides of the Schrödinger equation, which reads then overlap with the state from left and make use of the Schrödinger equation again. Given that the eigenstates of the Hamiltonian always form an orthonormal basis, the cases of m equals n and mn can be discussed separately. The first case will lead to the first theorem and the second case to the second theorem, which can be shown immediately by rearranging the terms with the differential rules given by the Helman-Fineman theorems. The perturbative correction to the energies and states can be calculated systematically. Correction of energy and state to the second order. The energy correction reads the first-order derivative mu n is given by the first Helman-Fineman theorem directly. To obtain the second-order derivative mu nu n, simply applying the differential operator mu to the result of the first-order derivative, which reads: note that for linearly parameterized Hamiltonian, there is no second derivative mu nu h equals 0 on the operator level. Resolve the derivative of state by inserting the complete set of basis, then all parts can be calculated using the Helman-Fineman theorems. In terms of Lie derivatives, according to the definition of the connection for the vector bundle, therefore the case m equals n can be excluded from the summation, which avoids the singularity of the energy denominator. The same procedure can be carried on for higher-order derivatives, from which higher-order corrections are obtained. The same computational scheme is applicable for the correction of states. The result of the second order is as follows: both energy derivatives and state derivatives will be involved in deduction. Whenever a state derivative is encountered, resolve it by inserting the complete set of basis, then the Helman-Fineman theorem is applicable. Because differentiation can be calculated systematically, the series expansion approach to the perturbative corrections can be coded on computers with symbolic processing software like Mathematica. Effective Hamiltonian. Let H be the Hamiltonian completely restricted either in the low-energy subspace or in the high-energy subspace, such that there is no matrix element in H connecting the low and the high-energy subspaces, i.e., if let F mu equals mu H be the coupling terms connecting the subspaces, then when the high-energy degrees of freedoms are integrated out, the effective Hamiltonian in the low-energy subspace reads here are restricted in the low-energy subspace. The above result can be derived by power series expansion of. In a formal way, it is possible to define an effective Hamiltonian that gives exactly the low-lying energy states and wave functions. In practice, some kind of approximation is generally required.